Hello, welcome to my presentation for the Cloud Computing Practical 8 presentation where we deal with RabbitMQ. I'm going to go through each of the 4 tasks in turn, explaining what I had to do, the code that I used and what it does. So we'll start off with task 1. In exercise 1 we're asked to use Pika's syntax to declare and bind the necessary queues and exchanges and their connections. And the task describes the structure of the system as follows. In the diagram here we have one exchange, which is the assignment exchange. We have 3 queues, the result queue, the correction queue and the validation queue. We have 3 consumers, the module coordinator, the demonstrator and the teaching assistant, and we have 1 producer, which is the student. So to create that, first off we need to make a connection. So I instantiate this blocking connection to RabbitMQ, and then a single exchange is declared down here, which uses the fan-out exchange type. And this exchange type just means that messages are sort of mindlessly broadcast out to every consumer, and they ignore any routing keys that we use. We'll come back to routing keys in a later question. To route messages to specific queues, we use queue bind down here to bind our result, validation and correction queues to the assignment exchange that we just defined. And that was about it for task 1. All we had to do was define these things. For task 2 of exercise 1, we're asked to use Pika's syntax to define where each actor, which is the demonstrator, the teaching assistant, the module coordinator, should listen to and consume from. And to define where each of our actors should listen for messages, we use this basic consume method. You can see that I use this for each one of them. So in each of these we specify which queue to listen on. As described in some of the comments here, the demonstrator is listening on the correction queue, this one here. The teaching assistants are listening to the validation queue, and the module coordinator listens to the result queue. And each of these use the same parameters. The 4 parameters that are provided to the basic consume method are the queue. So we have queue correction, queue validation, queue result. And this is just the queue that we wanted to listen on. We have onMessage callback, and this is the callback function that we want to run when a message is received. We have auto-ACK true, and that's saying to automatically acknowledge a message when it's received. It's also possible to manually acknowledge a message. We can use the basic ACK method within a callback if we want to do that. And then we use channel.startConsuming. Actually, I should mention we have this consumer tag as well. I don't think it's really necessary to use a consumer tag, but it provides a unique identifier for the consumer, so I added it in anyway. And finally we have this channel.startConsuming down the bottom, which is a blocking function. It just starts an infinite loop of message consumption. And of course we have some, for this task at least, we have some very simple callbacks which run when a message is received by one of these consumers. All they do is receive a body and print out what they got. For exercise 2 then, we're asked to, using RabbitMQ and Python's Pika, implement the scenario described in exercise 1. We're asked to use 4 classes, which are student, demonstrator, teaching assistant and module coordinator. So in exercise 1 we already defined our queues and the exchange, and we defined the bindings between them. So to implement the scenario described in exercise 2, we first just need to create the classes that we've been asked to make. And the flow of messages in this follows the pattern of the student submits an assignment, the assignment is received by the demonstrator, which is listening on the correction queue. You can see that here. And the teaching assistant validates the assignment, and the validated assignment is published to the result queue, having been received by the module coordinator, which confirms it. So as an example, in exercise 2, here's one of the classes. The demonstrator class, as one of the actors, which is a consumer, it receives an assignment via this correct assignment method, and it changes the status from submitted to corrected. And very similar then we have a teaching assistant. has a validate assignment method instead. It's almost identical to the demonstrator, other than the status now is changed from corrected to validated instead. And again, the module coordinator has a confirm assignment method, and it's very similar. It just changes it from validated to confirmed. A student is unique among these classes. It's a little bit different in that the student is a producer, while all the other ones we've seen there are consumers. To act as a unique identifier, the student receives a student ID attribute, and the student's job is to submit assignments. So the submit assignment method receives a message as an argument to it, and it returns a JSON object which represents the student's assignment, which consists of a student ID, an answer, and a status. The status always begins as submitted, and then it changes as it progresses through the messaging queue. And other than having added these classes, the demonstrator, module coordinator, and the teaching assistant and the student, we also had to make some changes to the main.py file. Not too many, I suppose. Down the bottom, we had to instantiate a student, the class that we just created there. We get a student assignment via this submit assignment method. And we have this basic publish where we serialize the JSON object that we received from the student assignment submit assignment method. And this serialize, I just have two sort of utility methods up the top here, serialize and deserialize. Since the message is a JSON object, I need these utility methods to serialize and deserialize the object just to facilitate passing the JSON object around the messaging queue, because I wouldn't be able to just pass the JSON object as it was. It needs to be serialized. We also added, we already had these actually, but they weren't really implemented properly. We have these callbacks. We have one for the demonstrator, one for the TA, and one for the coordinator. And the structure of them all is pretty much the same. As an example, in the demonstrator callback, first thing it does is deserialize the body which it receives from the student down here. So obviously we're going to publish to the correction queue, and because the demonstrator is listening to the correction queue, then this callback is going to receive that body. So it has to deserialize the body because it's been serialized to JSON. And the conditional checks if the assignment the demonstrator received has the correct status. If it doesn't, it's ignored, and we print the output to say that it received an invalid status. Otherwise, if all is well and we get into this true part of the block, we print out what the demonstrator received. We run this correct assignment method, which just changes the status from submitted to corrected. And I've added this sleep just to add a 1 second delay inside this callback. And once it's finished with its processing, it publishes the updated assignment to the validation queue. And again, it serializes the body before it sends it through. And the teaching assistant and the coordinator are generally the same. Both methods receive this JSON object in the body. They have to deserialize it. They have to perform some operations on it. In the TA callback's case, it needs to validate the assignment. For the coordinator, it needs to confirm the assignment. And that's pretty much it for the changes that we made. To actually run this code, I'm sure it could have been run locally too, but I thought it would have been simpler to just use Docker. So I've got a Docker compose YAML script and a Docker file. And this script just defines two services. I got this from one of the previous RabbitMQ assignments. The first service that we define here is the RabbitMQ service itself, and that relies on this RabbitMQ image. It uses some port mappings between 5672 inside the container and 5672 on the local machine, and same again for 15672 between the local machine and the container, where one is for the actual messaging service and one is for the management dashboard of RabbitMQ. The other service is the Pika example, and that's going to be our actual code, which relies on this Docker file. And all we do in here is we install Python. At the top line we install Pika, which we need to interface with RabbitMQ. It copies all our relevant files, sets a Python path, and as soon as this container starts, it runs the main.py file. And just for convenience, I've also defined this PowerShell script, which deletes the containers, builds the containers, and runs Docker Compose up to start them, just to save me having to run those commands individually. So to have a look at what the output is like for exercise 2, let's say run .ps1. So now if I open up a terminal in this container, I can run ls and we see our files have been copied in. I can run that main file. And we notice here that sometimes an actor might receive an invalid assignment. For example, there, the first line, we can see that the demonstrator received an assignment with the status corrected. And so it has to ignore it because it was expecting an assignment with the status submitted. It doesn't want corrected. And this happens because we're using the fan-out type exchange. There's no particular order to which actor will receive which message. As I outlined previously, the fan-out exchange, it just sends it to every actor which knows about it. The root and keys are ignored, so this is to be expected, I suppose. But in the next exercise, we'll fix this. So for exercise 3, we need to split the demonstrator into two separate actors: data mining demonstrator and the cloud computing demonstrator, which each need to listen to their specific respective queues. And we want to ensure in this case that messages aren't repeatedly broadcast into all queues. And we want to optimize the system by dedicating a demonstrator to each specific module, being cloud computing and data mining. Each entity should also, we're told, only receive relevant assignments, which is unlike in the previous example we just saw, when some queues might receive assignments which weren't intended for them. So to implement this, make a couple of changes. Go into ex3. In here, when I declare my exchange, I'm no longer using a fan-out exchange. This time I'm using a topic-based exchange. By using a topic-based exchange in conjunction with routing keys, as we can see these here, we can specify where exactly our messages are to be sent. And so, in conjunction with this, when binding our queues to our exchange, we specify routing keys. So we say here, in this case, the routing key is results and validation, cloud computing, data mining. And by specifying these routing keys in a topic-based exchange, we tell the consumers where exactly the messages are to be sent, which stands in contrast to a fan-out type exchange, where messages are sort of mindlessly broadcast out to all available consumers. And if I run this time, we see we get a different output. So once that runs, we can see that this time no consumer receives a message which wasn't intended for. The cloud computing demonstrator at the top and the data mining demonstrator received their respective assignments. And assignments are sent from the demonstrators to the teaching assistants and then on to the module coordinator in the correct order. So in the way that I've used a topic-based exchange, it would in reality have been the same thing to use a direct type exchange. The topic exchange allows us to get very specific with the routing keys that we use. We can use symbols like an asterisk to substitute words in routing keys, or we can use a hash to match 0 or more symbols. We can use a dot symbol operator to specify features connected to a certain message. In my case, I didn't bother with that because we only have the 4. I didn't need to get very specific. You know, you might do something like, let's say, for example, if we had correction dot validation or something, we could say correction dot. Actually, it would make sense in the case of cloud computing. Maybe we could have done something like correction dot cloud and then correction dot data or something like that, but I didn't bother doing that, so it's sort of essentially the same thing as it would have been if I had used a direct type of exchange, at least it seems to me. But the key difference here is that the messages are being sent to exactly where you want them to, rather than just being sent out randomly. And finally, for exercise 4, we're asked to Dockerize our solution from the previous exercise. We have to use 6 containers, 5 of which represent each of our entities, that being student, data mining demonstrator, cloud computing demonstrator, teaching assistant, and module coordinator. And then we need to have an additional container which just runs RabbitMQ. So for this task, I've used this folder structure. Each entity in there has its own respective Docker file, a copy of a utility file, and a class file. So for example, if we look at the cloud computing demonstrator, we have the class file itself, demonstrator CC, a Docker file, and the utils file. And each one of these has this copy of the utils file. All that has is our serialize and deserialize methods from we saw previously. And we have this init method, which I just used for readability, so we can just run this init, which returns the channel rather than having to have these 3 lines of code in each one of our classes. To take the demonstrator itself as an example, all the classes follow a pattern quite similar to this one. So I've added this channel attribute to the class self.channel equals init, the init method that we described there previously. And I think that just makes it cleaner that we don't have to have that as a variable, a function that returns the channel or something like that. It's nice that it's a class attribute. Each class also declares an exchange. We have in the next line. You can see this time actually I'm using a direct exchange because it works out more or less the same as using a topic exchange in my case. I used a direct, but really the result is the same as it would have been with the topic. I've added this queue purge line just to make sure, it isn't really necessary I suppose, but just to make sure that any remaining messages which might have been left in the queue are cleared. I've moved each actor's respective callback into their class body. Which is cleaner than just storing them in main.py. And obviously we're running these as separate consumers in their own container, so they need to have their callbacks in their own file. I've added this consume messages function, and all that does is it acts to consume messages from the queue, and it starts consuming via the class's channel. All the other consumers follow this same pattern. More or less, well, the consumers follow the same pattern. So we saw the demonstrator cloud. The demonstrator data mining is almost exactly the same, just with its own callback. Module coordinator is the same, and the teaching assistant is the same. The only one that's really different, as in the previous examples, is the student. It's a little bit different. Just because obviously this one acts as the producer, so it needs to send something out to the other consumers. So I have this submit assignment method, kind of similar to the last one, just that we have the options can be data mining or they can be cloud computing. It returns a JSON object. Here it actually has a main method in this one because I'm going to call that as soon as the container starts running. inside main, one thing of note is that I instantiate a student. I set up a while loop to just infinitely create cloud computing assignments and demonstrator assignments and send them out to the queues that they need to go to. I just had to sleep 10 just, I suppose, to simulate some sort of a delay. Returning to the cloud computing demonstrator as an example, obviously you can see each of these also have a Docker file. So just to look at one of these, this is different to our original Docker file that we use in exercise 3, in that we only copy the files that are necessary for a single actor and run only the Python file that's needed for that actor in particular. So here all we copy is the demonstrator itself, the utils that it needs, and it only runs the demonstrator file itself, whereas previously we would have run main and then that in turn runs all the other consumers. So it's just one at a time for us in this case. But still the same, we need to install Python and Pika, same as we did before. The same structure is followed for the other actors. It's almost exactly the same. Module coordinator, we just copy the module coordinator file and we run module coordinator. The next significant thing that I had to change is to create pretty much a completely new Docker compose file, the YAML script. And in this much longer Docker compose script, we have to define 6 separate services, as we said. We define a service for each of our actors, being the student is here, data mining demonstrator, cloud computing demonstrator, teaching assistant, and module coordinator. And then we also have to have another container for our RabbitMQ service itself. To each of these containers, I've added the restart always attribute just to make sure they always try to restart on failure. And each consumer in here depends on the RabbitMQ service. Let's see, for example, where can we see that? The student is a bit different, but the other ones we see depends on RabbitMQ for the data mining demonstrator, and the same for the cloud and all the other ones. One thing of note here, you can see I have this depends on RabbitMQ condition service healthy, and I have this, if I can find it, I have this health check up here within the RabbitMQ container, and all that does is just continuously ping the RabbitMQ management page until it responds before starting the other containers. And that's just to make sure that the containers don't start before RabbitMQ is ready. So it just keeps pinging the management page running on port 15672 to make sure that RabbitMQ is ready. So that just means that other consumer containers are prevented from starting before that condition is met, because all the consumers depend on the RabbitMQ container on the condition that the service is healthy. Anything else of note? I also have down here, you can see the student itself depends on every other service, because the student, it being the only producer, it shouldn't send its 2 messages until after every other container is ready. So again, if I were to run this using our PowerShell script, so now we've got our RabbitMQ container running and every other one just started. So I can start to run these, sort of starting at the top level. We'll go module coordinator first. It's running. Waiting for messages. Start the teaching assistant. Now that's waiting for messages. There I can start our demonstrators. And now that's waiting for messages. Then our other demonstrator. And now that one's waiting for messages. And that's all of them other than our student. So now I'll move this to another screen for a second and open up all of these on the one screen so we can see. So we've got module coordinator, data mining demonstrator, cloud computing demonstrator, and the TA. And now just on my other screen I'm going to start the teaching assistant, or not, sorry, the student. Once the student starts, then it starts to send out its messages. And we can see they're all starting to receive them in the order that we want them to. You can see, for example, the demonstrator gets an assignment with the status submitted. It sends them on to the validation queue, and then the teaching assistant receives them from the validation queue. It corrects them, publishes the results. Up here we have the module coordinator, and the module coordinator gets them and changes the status to confirmed, and we're done. And that's pretty much it. Thank you for watching. Hopefully I went into enough detail. I'll go more in depth in my report than I did here in the video, I think, anyway. Thank you very much for watching.